So in this video, we're going to talk about the two most common types of compounds that we see in chemistry. They are molecular compounds and ionic compounds. And the distinction between these two types of compounds is made on the basis of the type of bonding that is present. So molecular compounds have covalent bonds in them. And so for this reason, sometimes these guys are called covalent compounds. And then you guessed it, ionic compounds, they have ionic bonds in them. So we're just characterizing these compounds on the basis of the types of bonds that are present between the different atoms that are there. So it's chemical bonds that hold atoms together in compounds. And the chemical bonds form as a result of electrons on different atoms interacting. And of course, this is going to be the electrons that are on the very outer surface of our atom, right? So these electrons that are on the edge of the atom, because when two atoms come together, and they're going to interact via their outer surfaces. So there's two main mechanisms that chemical bonds are formed by. One is the sharing of electrons. And when electrons are shared between atoms, what happens is a covalent bond forms. And the other mechanism by which bonds are formed is the transferring of electrons. And what happens there is electrons move from one atom to another. And when electrons are transferred, an ionic bond forms. So the first type of bonding that we're going to be talking about is covalent bonding, sometimes also referred to as molecular bonding. So you'll see the terms covalent and molecular used interchangeably by chemists. But covalent bonds or molecular bonds form when atoms share electrons. So the simplest kind of atom is a hydrogen atom, and a hydrogen atom has one proton and one electron. So it's really common to study hydrogen atoms. Now, the interesting thing that happens is that when two hydrogen atoms come together, they get stuck to each other. And we know this because we never observe hydrogen in nature as individual atoms. We always see it as H2 molecules. So the question becomes, why do hydrogen atoms stick to one another? So here we have two hydrogen atoms, and they're not stuck to one another. They're separated by a very large distance. And as I mentioned, each of these hydrogen atoms has one electron and one proton. The electron is orbiting the nucleus, which is comprised of just a single proton. So these guys come together, and what's going to happen? Their electrons and protons are going to start interacting, right? And what we know is that opposite charges, like the electrons, will repel. Similarly, the protons will repel one another. Sorry, like charges repel. I said that wrong, didn't I? But opposite charges will attract, right? So we're going to have a whole bunch of forces going on as these things come nearer one another, and the closer they get, the stronger those forces are. So the electrons will repel one another, the protons will repel one another, but the electrons on one atom will be attracted to its own nucleus plus the nucleus on the other atom. Similarly, the electron on this guy will be attracted to its own nucleus, but also the nucleus or the proton on the other atom. So yeah, that's what's going to happen, right? So we're going to bring these atoms together, and then the space in which the electrons are moving is going to kind of coincide. They're going to be near one another, all right? So what we find happens is when we bring these two atoms near one another, they get stuck together, and the electrons end up exactly sort of spending most of their time sitting in between the two nuclei with a very, very precise distance between these two protons here. And this happens every time. They always get stuck in this arrangement. And so what's happening here is that there's an overall attractive force between the two nuclei, And what it is this proton here is attracted to these 2 electrons. And it's a pretty big attraction because there's 2 electrons tugging on 1 proton. And similarly, this proton here is also attracted to those 2 electrons. And it's a fairly short distance there, and it's 2 electrons, so it's a big attraction. Now, there is a little bit of repulsion between these 2 protons, but it's a +1 being repelled by a +1, so that makes it fairly small. And also, it's at a pretty big distance, right? Similarly, the electrons kind of do repel one another too. They want to get out of each other's way, but it's a -1 with a -1, so it's not as big as these 2 lots of the +1 with a -2. So overall, the attractive forces win out, and these atoms get stuck together. Now, they get stuck together, as I mentioned, with a characteristic distance between the 2 nuclei that we call the bond length. Now, I'll just explain this here. So if we put energy here, what we find is that there's kind of a really good arrangement there where we have this sort of like just the perfect bond length. And if we, this is the distance between the protons. And if you kind of bring them any closer together, then the protons start repelling one another a lot because they're closer now. And that destabilizes the system. And similarly, if you kind of like pull them apart, then this attraction towards the electrons becomes weaker, and again that destabilizes the system. So it always kind of settles down into this kind of like energy, what we call an energy minimum, where we just got the sweet spot where we're maximizing the attractive forces and minimizing the repulsive forces. It's kind of like if you have a house, you want your house to be big enough that, you know, all of your family members are happy, they get to see enough of one another, but it's not so cramped that they fight. You want to maximize all the good stuff and minimize all the bad stuff, and there's kind of a sweet spot for that. So these guys get stuck because they share electrons, right? They get stuck to one another because they share electrons, and that is a covalent or molecular bond. So covalent bonding or molecular bonding occurs between nonmetals. So if you have a compound that only has nonmetals in its formula, then you know that it is a covalent or molecular compound. Now, the atoms that are covalently bound together, they form an uncharged species that's called a molecule. It's like a little bundle of atoms. Each of the atoms in there are stuck together. Right? There's a water molecule. Here's a carbon dioxide molecule. All right. Now, it gets a little bit more complicated than that, and we're going to delve into that now. You can also covalently bond nonmetals together to form a charged species, and that's referred to as a polyatomic ion. So the atoms within a polyatomic ion are covalently bonded to one another, but the whole assembly of atoms has an overall electrical charge, and so it is referred to as being an ion. So the atoms that are present in molecules, or we could say all polyatomic ions to be fair, are chemically bound to one another. You can't separate them by physical means. You can't use a magnet, you can't use a filter to separate out the different atoms that are in a molecule or a polyatomic ion. So that's an important thing to keep in mind. So different molecular compounds represent different ratios of atom types bound together. So for example, this is a hydrogen peroxide molecule, and this is a water molecule. Now, these guys, they both contain hydrogen and oxygen atoms connected together, but there are different ratios of hydrogen and oxygen atoms, and as a result, these two compounds have different physical and chemical properties. They're going to have different melting points, different boiling points, different reactivities towards other things. So for example, water, we all need water. We have to drink water or we die. Whereas if you used to drink pure hydrogen peroxide undiluted, it would very, very quickly give you a mouthful full of blisters and quite possibly damage you to such an extent that you die. Now, there are 7 elements on the periodic table that are always found in nature as these diatomic covalent molecules, just like hydrogen, right? When these atoms bang into one another, they get stuck to each other as a result of the sharing of electrons. So these guys here, what we call the diatomic 7, they're always found as these diatomic molecules. Now, there are another couple of elements that are always found as more than one atom that are not monatomic elements, and they would be S8 and P4. And S8 is interesting. It's 8 sulfur atoms joined together in a ring. And P4 is also kind of interesting. Phosphorus has a variety of forms, but the one that I'm thinking of is where we have 4 of them connected in what we call a tetrahedral. So we've got 4 of the phosphorus atoms at the corners of a triangular-based pyramid. We need to recognize that covalent compounds have a wide range of melting and boiling points. So you're going to find covalent compounds that are solids at room temperature. Some are going to be liquids, some are going to be gases. You really can't imply anything about the nature of the bonding. You can't identify whether covalent bonding is present on the basis of melting or boiling point alone. Okay, so that's a good review of molecular or covalent compounds. Now we're going to talk about ionic compounds. So the important thing to recognize is that as neutral atoms have equal numbers of protons and electrons, they have no overall electrical charge. However, it's kind of obvious that if an atom loses or gains one or more electron, it will become electrically charged, and because it will have either an excess or deficit of protons, and it will form a species called an ion. We've heard this before in previous classes. If an atom loses one or more electrons, it forms what we call a cation, and you've all heard my bad joke about this. They're called cations because they are positive. And a classic would be a sodium atom losing one electron to form a sodium plus cation. So the elements that like to lose electrons and form cations are hydrogen and the metals, which is most of the elements in the periodic table, right? So that's what happens. And the thing to keep in mind is that for every electron lost, your cation gains 1 positive charge. So as long as you keep that in mind, you will be fine. Now, if an atom gains 1 or more electrons, then it's going to form a negatively charged anion. And there's a little sort of memory aid for this one. Anion begins with the 3 letters ANI, so you can remember that as A negative ion, A negative ion. And the elements that form anions are the nonmetals. So all of the nonmetals form anions. Ions that are formed from a single atom are called monatomic ions. So that is a monatomic ion. This guy is a monatomic ion. Barium 2+, we just looked at before, is a monatomic ion, but NH4+, we looked at before, that's going to be a polyatomic ion. Okay, so how do we know the charges on an ion? How do we know how many electrons a metal or non-metal will lose or gain? Well, for the representative elements, we can figure this out pretty easy. The representative elements always lose or gain electrons to obtain the same number of electrons as the nearest noble gas. Now, once they get a noble gas configuration, they stop becoming reactive, right? Because, you know, they lose or gain electrons until they become like a noble gas, and then they just stop becoming reactive. And because at that point they have an electron configuration that looks like a noble gas, and what do we know? Noble gases are unreactive, so they're just going to stop reacting. So that's our key to figuring out what these charges are. Now, something to be aware of is that the nonmetals are all representative elements. So we can always figure out the charge on an anion just by looking at the periodic table. We can always figure that out. So we always know charge for anions. Every time we'll know that. Okay, so there's never any confusion. Not all of the metals are representative elements, but those metals that are in group 1A, group 2A, and group 3A, we can figure out the charge for those guys. We always know the charge for those. So for a lot of the elements, we always know what kind of ion they're going to form. So let's have a look at this. Here's sodium here. It has 11 electrons. Its nearest noble gas, well, there are two that are near it. Neon has 10 electrons, argon has 18, so neon is its nearest noble gas. So what does sodium like to do? It likes to lose 1 electron so that it has the same number of electrons as neon. Let's go to another metal and repeat the process. Here's calcium. Calcium there, you can see it has 20 electrons. So what is its nearest noble gas? Well, we just look over here. Yeah, it's got to be argon is its nearest noble gas, right? Argon has 18 electrons. So for that reason, calcium loses 2 electrons and forms a calcium 2+ ion, which has the same number of electrons as argon. Let's have a look at aluminum. Here's aluminum here. 13 electrons. What one is the nearest noble gas? The nearest noble gas is neon. So what's going to happen is aluminum will lose 3 electrons, leaving it with a 3+ charge. Pretty simple idea. Okay, so we said that the nonmetals gain electrons until they have the same number of electrons as the nearest noble gas. So here's phosphorus here. It's got 15 electrons. So the nearest noble gas, it's not 36, it's not 10, it's got to be 18, right? Yeah. So 15, it's got to gain 3 electrons. P plus 3 electrons. So it gained 3, ends up with a 3- charge. Okay. Here's the other example, oxygen. Oxygen has 8 electrons. Its nearest noble gas is 2, 10. Nope, it's neon with 10. So what's going to happen? Oxygen, it's got its 8 electrons. It's going to gain 2 electrons, form O2-, which has 10 electrons. Same as neon. Okay, so that's it. It's pretty easy. So the nice thing to recognize is that for any of the nonmetals, right, we can always figure out the charge because they're all representative elements. And then for group 1A, 2A, and 3A metals, we can also figure out the charge because they are representative elements. So yeah, it's not too bad, right? We can do this. Okay, I know you're all thinking about it. What about the transition elements? We'll get there in a moment. So we have to recognize how the ionic bond forms. And how an ionic bond forms is when a metal reacts with a nonmetal and there is a transfer of electrons from the metal to the nonmetal. Right? Now the type of ionic compound that we're going to be talking about is what we call a binary ionic compound, where we have one cation and one anion. one cation type, I should say, and one anion type. Sometimes we have like multiple cations, but they're all of the same type. Sometimes we'll have multiple anions, but they're all of the same type. So what's going to happen is there's a transfer of electrons from the metal to the non-metal. So we're going to have a metal come near a non-metal, and instead of sharing electrons, what's going to happen is electrons are going to move from the metal to the non-metal. As a result of the transfer of electrons, the metal will get a positive charge and the non-metal will get a negative charge. What happens to positive and negative charges? They get stuck together. So after this transfer of electrons, you don't have individual atoms anymore. You're going to end up with an ionic compound, right? Because the ions produced as a result of the transfer will attract one another. Okay, so what we know is that sodium with 11 electrons loves to lose one electron and form a Na plus cation. Similarly, chlorine with 17 electrons loves to gain one electron, end up with 18 electrons like argon, and form a Cl minus anion. Okay? Now, what happens when a sodium atom bumps into a chlorine atom? Well, what's going to happen is this. An electron gets transferred from the sodium to the chlorine. Let's break this down into steps. An electron goes like that. As a result, a sodium ion is formed and a chloride ion is formed. And what are those guys going to do? They're going to attract one another, boom, and get stuck together, right? So this bond forms as a result of the transfer of electrons. Okay. Now, an interesting property of binary ionic compounds is because this bond is very, very strong and it's really hard to separate out these anions and cations from one another, all binary ionic compounds are solids at room temperature. Now, how strong is this bond, and what are the two factors that it depends upon? It depends upon two things. It depends on the product of the charges of the ions. So as the charges of the ions go up, so as we go from +1 to +2 to +3, from -1 to -2 to -3, as the size of the charges involved increase, the bond gets stronger, and that's not too surprising. The other thing that happens is that as the ions involved get bigger and the distance between the centers of the ions gets bigger, the bond strength gets weaker. So itty bitty ions really with high charges are going to have really strong bonds, and then big ions with low charges that are their centers are further away, when they come together, they're going to have weaker bonds. This is important for Chem 162. Okay, so ionic compounds have no overall electrical charge. We didn't create or destroy any electrons. What happened is we just moved electrons from one place to another. So we start with a bunch of neutral things, and then we just move the electrons around, so what we end up with has no overall electrical charge. Ionic compounds are different from molecular compounds in that there aren't any molecules in an ionic compound. In an ionic compound, what you have is an approximately infinite repeating pattern of anions and cations, and the anions and cations are organized in such a way as to maximize the attractive forces and minimize the repulsive forces. And typically, ionic compounds have really high melting points, generally greater than that for covalent compounds. Now, again, in Chemistry 162, we're going to spend a lot of time looking at how these ions are organized in these infinitely repeating crystals to maximize the attractive forces between the particles involved. But an important thing to remember is that the microscopic structure of these crystals, which is what these guys are, reflects the external structure. So reflects the macroscopic structure. So if you have a look at some salt crystals, just table salt, pull them out, you'll find that they're all little cubes, right? And the reason for that is because the ions are organized in a cubic fashion at the microscopic level. So we need to know how to write the formulas for ionic compounds. And the formula for an ionic compound indicates the simplest ratio of anions and cations that result in electrical neutrality. So what that really just means is that the total positive charge has to equal the total negative charge. And the easiest mechanism for getting this ratio is to use the crossover method. So here we go. Here we've got, and in the crossover method, what happens is the superscript, the charge on one ion, becomes the subscript or the number of the other ion. So we've got sodium 1+ here combining with oxygen 2-. So what that tells us is that we need 2 sodiums and 1 oxygen. And that's going to be the formula there. Now, we're always going to give the simplest ratio of anions to cations. So you can see if our ions have the equal and opposite charges, what happens here? So we've got a calcium 2+ with an oxygen 2-. So we do the crossover and we would decide that we need 2 calciums and 2 oxygens. There it is there. But we can see that this is not the simplest ratio. We can divide through by 2 the common multiple there, and then this is the correct formula over here. So something to keep in mind is if the charges are equal, you'll always have a 1-to-1 ratio of the ions. Okay, so you don't actually need to do the crossover if the charges are equal. You know that at the end of the process, they're just going to be together in a 1-to-1 ratio. So if your charges are equal, don't worry about the crossover. You know they come together in a 1-to-1 ratio. So let's look at a more complex one. Here we've got Pb4+ combining with S2-. We're going to do crossover here. So that means that we'd need 2 leads and 4 sulfurs. And you can see that this is not the simplest ratio. I can divide through by the common multiple of 2, PbS2. So we're always going to give the simplest ratio of ions that result in electrical neutrality. When you're a beginner with this, sometimes people will always go through and double check that we do really have the same, that the positive charge equals the negative charge. So that gives +4, and then S2-, S2-, that gives -4. So sometimes people will go through and double check that at the end of the process. Okay, so that's a short review of molecular and ionic compounds. We talk about the origin of these 2 different types of bonding, and we learn a little bit about how to write the formulas for ionic compounds. I hope that the video was helpful, and yeah, good luck.